So on to the next round of presentations. First up, we have David Jonson. David was born in South Africa and he is a mechanical engineer specialising in the design and analysis of composite structures. He spent most of his career in the academic sector, focusing on research, and has also consulted as a practicing engineer to companies and institutions in the defence and industrial sectors. He was part of the South African Shosholoza design team that campaigned for the 32nd America's Cup in 2007, and more recently the British challenger for the 35th America's Cup, which is what he's going to talk about today. He enjoys sailing and mountain biking in his spare time, so I'm sure he had a keen interest in the last presentation from Rob. So over to David.
Right, thanks very much. As you've heard, my name is David Jonson. It's a bit confusing at the moment. I work for a company now that's called Ineos Team UK, which was the former Land Rover BAR. I'm unbranded because our marketing department is a bit sensitive to the clash of sponsor titles. But I'll be talking about Land Rover BAR's experiences in the previous Cup, particularly in regards to the work we did on this particular type of yacht, the America's Cup 50-foot foiling catamaran. A lot of the work I'll be talking about was done in collaboration with JLR and Martin's team at GRM. So for more technical questions, I'll defer to them. Right, the America's Cup. Well, it's the oldest yachting trophy, well, the oldest international sporting trophy in the world, and really represents the pinnacle of sailing technology. It was first offered as the Guinea Cup, the 100-pound cup, in 1851, and was for a race around the Isle of Wight, which the American schooner America won, and that was the last time we saw the America's Cup in the UK. We have the privilege of looking at the Isle of Wight from our offices, so we have a permanent reminder of that event. The American teams that were representing the New York Yacht Club successfully defended the Cup for 132 years, so-called the longest winning streak in sport, until the Australians won it in 1983, and then since then it's changed hands a few times, and it's been held in various locations. Emirates Team New Zealand won it at the last event, which was held in Bermuda, and they are now the current defenders and responsible for organising the next competition. If I'm not mistaken, the Land Rover BAR's bid for the America's Cup, or challenge for the America's Cup, was the 21st time that the British had challenged for the Cup in its history. So as far as the actual challenge is concerned, you basically have one chance to get it right. We don't race a circuit of races typically. We may race in other yachts, but we don't race the competing yacht a number of times. We have one Challenger series at the end of at the event, which selects the Challenger, which then goes up against the defending yacht. It's very much a technical race, so as much as it is a sailing race, it's a race of technology as well. You try and maximise the advantage that you have through selecting appropriate methods and so on to gain a competitive advantage. You're always leaning on leading edge, advanced technology where you can make it work. We're under enormous time pressure to deliver what's effectively a prototype yacht that has to compete, which has to be very competitive at the end of its development. We typically have very limited opportunity to physically test components due to the time pressures, but also the rules typically stipulate limitations on the use of wind tunnels and testing tanks and that type of thing to do physical testing. We're subject to regulation through the rule structure. The rules can be fairly complex, So there normally are quite a few constraints that we have to adhere to as part of the measurement process. And then obviously it's safety critical. In previous generations of the yachts, they were fairly slow but very highly loaded. These yachts are particularly quick, up to 50 knots, and deaccelerating the boat from 50 knots to 12 knots in a space of a boat length is pretty severe, and obviously poses a safety risk to the sailors. You can see that they're fully kitted out in body armor and helmets and such like. Right, so as far as the Land Rover BAR's effort was concerned, we had up to 50 technical staff working in various areas. We were typically grouped as designers and naval architects, looking after the overall picture, performance and prediction and data analytics. This was a very important component of the program. The fluid dynamicists and the CFD engineers, structural and composite engineers, and then the mechanical, hydraulic, and electrical design. They're obviously all tightly interlinked. We all sit in the same room, really, or the same space, and there's constant communication. But for the purposes of organization, they're typically separated out into these groups, being led by a team leader, and it proved to be fairly efficient. So as far as the yacht itself is concerned, it's 50 foot long. It's a hydrofoiling catamaran, so it foils on the, you can see the hydrofoil poking out the bottom of the yacht. Its overall dimensions, it needs to fit within the constraints of the rule. The technical freedom that we had in this particular iteration of the America's Cup was the hydrofoil design, the control systems, the wing structure, and the aerodynamics. The platform itself, what we call the platform, the catamaran hulls and the cross members and so on, that was all predefined as part of a one design package. We were allowed to add a certain amount of structure if we needed to, if we thought we might need to stiffen it or strengthen it, but we were not allowed to remove anything. All the flying surfaces are actuated hydraulically, or typically hydraulically, but all the power needs to come from the sailors. We're not allowed to have any stored energy aboard, batteries and so on, or capacitors. We're able to sustain speeds up to 85 kilometers an hour, which on water is particularly quick. But there's no fly-by-wire, there's no feedback loop, and that's stipulated in the rules. The helmsman has constantly, he's part of that loop, so he has to take the corrective action, and that's an ongoing, he's fully occupied keeping the boat flying. And as I've said, all the power must be human. As far as the catamaran is concerned, it's fairly basic. You've got the aero force that's trying to tip the boat over, and then you've got the gravity force that's trying to keep it up. So that's the balancing act. You've got a hydrodynamic force which is generated by the hydrofoil, which keeps it from sliding downwind, which enables you to sail efficiently upwind. And then you've got the rudders which balance out the pitch moment in the boat. It's fairly straightforward in terms of control. You've got the dagger board, which is able to cant in and out. It's able to rake forwards and backwards, and that's our main control for heave in the boat, what we call heave, but the fly height of the boat. And then the rudders, as I've said, balance that out. So you're flying on 3 foils. The hydrofoil, the main hydrofoil and the dagger board, as we call it, that rakes forwards and backwards, all under human power. In our boat, each team configured the way they controlled the systems differently, but in our boat, the helmsman controlled the steering of the boat and the board rake. The other significant feature of the boat is that we could have what we call rudder differential. The rudders could be set at alternative angles of attack, which simply meant that we were able to pull down with the rudder on the windward side, generating more righting moment and developing more power in the boat. So just from the point of view of loading and so on, sort of maximum mass compression being applied is around just over 13 tons. So that's trying to break the forward beam really. And then the other very important load is the downforce that you're generating with the rudder here. We generated a maximum of about 1.5 tons of download here, which is equivalent to about 18 crew members sitting on that corner of the boat. So we typically sail with six crew, so you have an additional 18 sitting on the corner there. So you can imagine the loads and so on that it generates are fairly high. So at the risk of simplifying things, just in terms of the performance differentiators, we're really aiming to maximize thrust and minimize drag. That translates into sailing around the course in the quickest possible time. You need to have the right setup, so you need to be able to reconfigure your appendages and so on for the right conditions. And you obviously need to minimize mistakes. You need to race smart. You need to get around the course. You need to make the right decisions. And obviously, we also need to stay in one piece, which is pretty much the responsibility of the structures people. Just from the point of view of the simulation side of things, we try and simulate as much as we can. As I mentioned, we're limited in terms of the amount of physical testing we can do, but we need to cope with the real world. Okay, so there are often load cases and so on that we don't necessarily capture, and we need to be able to respond quickly. We need to be able to do fairly major repair work very quickly. We don't have time to analyze. There was a repair that was done overnight during the racing. We crashed with one of the other teams and put a big hole in the bottom of the boat. In terms of specific, I'm just going to focus on really two specific areas of work that we did, which involved a fair amount of simulation. That was the wing and the hydrofoil. As far as the wing is concerned, it's really the engine of the boat, and it consists of three elements: the flaps, three flap elements, and that really, the flap rotation controls the twist profile, if you will, of the wing, which controls the center of effort. The lower we can pull the center of effort in the wing, the lower the overturning moment and the more power we can generate. And then the angle of attack of the wing is just simply what we call the wing sheet, which is attached to the back of the wing. It alters the angle of attack of the wing. We also have passive control, where membrane deflection, the wing is covered in this plastic membrane, and the membrane deformation plays a role in the pressure distribution around the wing. And then also the way the actual main element in the flap actually deform. And then the key performance differentiators with the wing are maximizing the drive force, minimizing the drag, rapidly being able to change the twist profile in the wing, being able to do that in different ways. We have this term for linear and non-linear twist, which is exactly what it says, and then it must be energy efficient. All the energy comes from the sailors, and besides powering all the hydraulics, any control that is exercised over the wing must also be supplied. The energy for that must be supplied by them. I'm not going to talk too much about that. It's self-explanatory. The wing, as far as the design space is concerned, it's all one design. The main mast, as it were, is one design. Everything behind that is up to us, except for the shape. We need to conform to the shape. Everything, so the structure behind the main element in the shear web is open, and the target weight is around 445 kilograms. We developed a low fidelity tool set, which was really just a vortex lattice code coupled with a beam element model representation of the wing. This was done to really enable very quick turnaround analyses. We used this to effectively optimize the various structural components of the wing, of the flaps. We have these unidirectional beams which control the stiffness of the wing. The stiffness of the flaps. They're only supported the flaps each are supported at the top and bottom, and they deflect under the load. So optimizing these unidirectional planks is quite important in terms of minimizing the weight. That just gives you an idea of the deflection of the flaps, and just in terms of the distribution of planking thickness, selecting trailing edge deflection, which was acceptable from a CFD point of view and a drag point of view, translates to an optimum design. We also investigated the use of intermediate hinge points to control the deflection and the weight of the flap. Obviously, it's deflecting along its span, so the use of an intermediate hinge point is quite advantageous from reducing weight, but it does introduce an additional moment in the middle of the flap, which is, you can see here in terms of the deflection of the flap. What that really translates into is a weight for no intermediate hinge of about 1.7 kilograms. Just as an example, with the intermediate hinge, we were able to bring that right down to 0.25, but we had to spend some additional weight in terms of satisfying the higher stresses and the increased deflection that was caused by that. So we, at the end of the day, accepted the additional weight penalty with the no intermediate hinge. We also found that the trailing edge deflection on the flap, the fact that it was deflecting through around 50 millimeters, was not a significant aerodynamic driver. Also in the top flap, the twist profile, because of the shape of the wing, is distinctly non-linear. So trying to optimize that shape, you can see the sort of non-linear profile was quite important. So you can see some very lightweight skins, sort of 40 grams of carbon. So in the bottom of the wing of the flap, we've got a sort of 0.08 millimeter skin thickness. So keeping it from buckling and so on is quite important. So optimizing it, we got more or less as linear as we could get, which improved the twist response of the wing quite significantly. We also did some sort of rough topology optimization on the ribs. There are a lot of ribs in the structure and they consume quite a bit of weight. This really came down to a buckling constraint and optimizing the shape of the cutouts. So again, we used the VLM model for that and generated some optimum shapes. You can see that for different parts of the wing, you have various different shapes. Theoretically, we could do that for every single rib and really minimize the weight. They're all laser cut, so that is a distinct possibility. Turning to the high fidelity toolset, which we worked with extensively with JLR and Martin's team. This was really coupling a full 3D model of the wing together with a full RANS CFD. The most significant feature of this was the coupling was the use of the membrane, which we did not have represented in the VLM model. So just you can see here, the heating is used to control, heating of the membrane is used to shrink the membrane, which controls the deflection. So you can see with the heat cycles here how that deflection decreases in the model. And this is for the high pressure side. But then you can see, once coupled and being loaded, you can see the ballooning effect that you get with the membrane. This is an experiment that was run through the back where the membrane wasn't glued to the ribs, and you can see that separating out there. We did that basically to test whether the ballooning effect would be a significant performance driver. And here you can see some results of that. So the increased acceleration around the membrane bulges here, and it creates a high driving force provided that the wing is correctly trimmed. In terms of the hydrofoils, these are the most critical performance component on the boat. They're driven very hard structurally. The hydro guys obviously want to get the foil as thin as possible so it doesn't cavitate, and the structures guys want to get it as thick as possible so it doesn't fail. It's particularly sensitive to very high loads when it's mishandled, and that normally means that the guys are dropping it with a negative angle of attack, which pulls it out of, tries to pull it out of the yacht, and puts a negative load on the foil. And because the elbow is a full carbon unidirectional, it tends to put very high through thickness tensile stresses in the elbow and fails the elbow area. For that reason, we were particularly interested in studying the reverse load event. So we then worked with Martin's team in trying to understand this. So we simulated a board drop event at speed, and investigated the use of elastiner, typically with the ALE functionality. So we've got the water represented, the board represented, and then dropping into the water. So you can see that it gives a fairly realistic response. There are some caveats to do with mesh density and so on, but it was fairly encouraging. You can see the effect of mesh density on that behavior, and obviously the need for a small mesh to capture the drag, capture the loading correctly. This is just a little bit of detail on model construction, so based on a solid model, and with the ability to put strain gauges in strategic locations which matched our gauge positioning. So it's successfully running. There's a lot of refinement that needs to still be done, and it's an ongoing area of development. Right, just in terms of the lessons learned, you really need to have the correct combination of low and high fidelity tools. You need to make quick decisions. Waiting too long for a result is very time consuming. And then you need to have sufficient time to allocate to developing the tools properly before you use them in anger. We had a few, we wasted quite a lot of time with errors and so on, which we needed to make sure that we avoided. And then obviously hardware system optimization is very important. So what's next? It's foiling monohull. We're still working on getting this concept worked up, but it's very similar in terms of the anticipated loadings and so on. And again, we're fairly restricted in terms of the amount of, well, we're more restricted in terms of the tank testing and so on that we can do. So we're going to have a much higher demand for some accurate simulation work. Thanks very much. I've covered that very quickly, and hopefully you've got an idea of what we've been up to.
Thank you, David. Spot on to time as well. Any questions for David while we've got him on the stage? Go on then. Go on then.
Not technical, the engineering actually, but you said that obviously everything is, the energy comes from the group.
Yeah.
How do you quantify that in engineering? You know, if we like power a motor to turn something, how do you decide what power you get from the group?
Yeah, there's a full energy budget that's normally worked up. So the sailors go through a calibration process where they, certain sailors have a certain output. So they definitely are graded in terms of what they can put out. We have a test rig. Yeah, we have a test rig that the sailors. We have a grinder. So that you can see not so clearly on this picture, but there are a number of grinding pedestals in the boat which drive hydraulic pumps. And the sailors, we simulate that process, and we develop the energy budget around that. So in the last series of races, you saw that when the conditions were particularly rough, a couple of the boats actually ran out of power. They couldn't race anymore. The pressure in the hydraulic system dropped too low. So it's absolutely crucial that is properly mapped out.
Any other questions?
Does that mean the hydraulics have an accumulator?
Yes, they do. We're not allowed to have an accumulator though on the next series of boats, but the appendages are now, we're allowed to control that with a battery, electrical system with a battery. So anything above the water is now sailor powered.
Last year in Rover, I think 2 of the teams had pedal-powered grinder.
Yes.
Like a static bike, but everyone else had arm powered. So how did you make that decision? And what is the next iteration? What are you choosing this time? And how is that whole sort of process working?
Yeah, there was. It was an obvious possibility at the beginning. We discounted it because the sailors felt that they wouldn't be able to cross the boat. It wasn't a practical concept. They wouldn't be able to cross the boat, get into position in time and powering the system. They felt that would just take too long. But obviously the New Zealanders discovered that it wasn't, and it's a lot more efficient. What they did say when they won the competition, what they did say in developing the next rule, that they would try and outlaw the psych laws, which they called them psych laws. So now they've come up with this term that, with this clause that everything must be powered by hands. But there's a little bit of leeway in that, so we'll see where that goes.